Oh my goodness. He's given up on the actual instruments and he's using his own face as an instrument. Oh my god, I think I might like banging on the bucket.
Oh, you like the bucket, Mr.
Well,
Sam?
no. I think maybe a little more than that, but not necessarily that today. Okay, let's do some chemistry, Mr.
Should we do
Bergmann.
chemistry?
We probably should, yeah, because we
We shall do
don't want
chemistry.
you quitting your day job.
I'm not going to quit my day job. Okay, we have podcast for point 1. We are studying chemical reactions. We're going to study chemical reactions, but interestingly enough, we are going to not start talking about chemical reactions. We're going to talk about electrolytes and non-electrolytes, solutions, and how to make a solution.
The reason we're going to do that is most of the not all, but most of the reactions we're going to do in this class happen in solution. They're going to happen while they're dissolved in water. So we need to figure out how that happens.
When it's dissolved in water, Mr. Sams, what is that called?
That's called a solution. And the type of solution is an aqueous solution.
Yeah.
You could also call it a homogeneous aqueous solution.
That is correct.
Those are terms we're going to use synonymously.
Okay, so before we do this, we've got to define a few terms. And should be review for most of you. But if not, hey, you're going to learn it right now. That's pretty cool, huh?
Mm-hmm.
When we have a molecule that is polar, what does that mean?
Polar means it has a positive end and a negative end, and we're talking about like a partially positive charge. It's not a full-blown charge like an ion is with the transfer of an electron, but it's got a distinctly positive and distinctly negative.
What causes
portion.
that, Mr. Sams?
That's going to be due to an unequal sharing of the electrons in that covalent bond.
You see, for example, the water molecule that I'm drawing here on the screen, it has the hydrogen here has a net positive, or we say a slightly positive charge, and then the positive charge kind of resides between the two hydrogens, and then the oxygen has a net negative charge, or slightly negative charge, and that causes it to have a polarity, and so that's what we're talking about. So as you can see, water is a polar molecule because it has a net charge differential. I like to call them like little tiny itsy bitsy tiny little magnets. That's what they are, you know. Yes, indeed.
Okay, nonpolar molecules, obviously by the name being indicated, do not have polarity. Therefore, all the charge within that molecule is evenly distributed.
They're not polar, so charge is evenly distributed. Can't spell today or talk either. Distributed.
Right. So within all the covalent bonds in those compounds, all the electrons are being shared equally amongst all of the components of the bond.
And I think I'll use a fresh screen for ionic compounds. There's not enough room. So an ionic compound is what, Mr. Sam?
That's when there's a complete transfer of electron from one atom to another atom, and then it bears a full positive or negative charge, depending on if it gained or lost the electron. Now remember, electrons are negatively charged, so if something has a negative charge, it gained an electron. Now it might sound a little bit counterintuitive, but them being negative, you have to treat them as such.
So kind of here's an example I'm putting on the screen you want to copy down. Sodium, for example, has one valence electron, if you recall that.
Mm-hmm.
What he will do is he will give his one valence electron to the chlorine atom, and actually the chlorine atom gets now 8 electrons. I'll draw the electrons as black, but the extra electron that came from the sodium will be blue. And then what happens to the chlorine there, Mr. Sam?
Well, since it has an extra electron, it's going to have a -1 charge.
And then the sodium, by losing an electron,
is going to get a +1 charge. Now we have things that are positive and negative, and as we know, opposite charges are attracted to one another. So the positive sodium will be attracted to the negative chlorine. Hey, there, chlorine and sodium.
So sodium and chloride likes sodium likes chloride because they have opposite charges. You know, opposites attract.
Of course.
And then they have deep attraction for each other. Yes, indeed. It is very, very interesting.
So then they stick together, and you have alternating positive, negative, positive, negative, positive, negative ions.
Yeah, actually, let me go back to another blank screen. With this, the ionic compound, the interesting thing that happens is the sodium is connected to the chlorine, is connected to the sodium, is connected to the chlorine, is connected to the chlorine, is connected to the sodium. You see,
Shin bone connected to the
thigh bone.
Yeah, it's not quite, but it's alternating. It's not just one sodium and one chloride. It's a whole slew of them together, and overall, the lowest whole number ratio is 1:1. But we could have 1,000,000 sodiums and then 1,000,000 chlorines, or chlorides in this case,
Yeah,
Either way, it's still NaCl.
And note that the chloride, it was chlorine, and it became chloride when it acquired the charge.
Yes.
So that's kind of the point of that. All right, back on task a little bit. When an ionic compound dissolves in water, you have this picture in your skeleton notes. Essentially what happens is, if this is the, in fact, this particular picture right here, shows we have the chlorines and the sodiums all arrayed. This may be a different compound now that I look at it. But anyways, each color represents a different ion. Probably blue is a cation and the green is the anion. And what happens is, if you can kind of see in the picture above here, is that these little water molecules surround them.
Right. So if the ion is negatively charged, the positive portion of the water molecule is going to surround it, meaning the hydrogen part of the water molecule will be attracted to the chloride. And then for the sodium, since sodium is positively charged, the negative portion of the water molecule will be attracted to the sodium ion.
You know, I used to play a game. You guys ever played this game? Maybe you have. I used to be like this youth pastor guy, and we'd have this game where we'd have these girls and these boys, girls and boys. They'd fight each other, so to speak. And basically the boys would all have to get into a big mass, and they'd have to hold on to each other. Tickling wasn't allowed, you'll understand. And they'd have to find some way, they'd intertwine themselves in some fashion, and you know, and the job of the girls was they were supposed to break them apart, okay? And how do you think, what strategy did they do that to break them apart? Because they're all this big mass, and arms are connected to legs, and legs are connected to arms, and heads are connected to arms, and we had this boy Tommy, and Tommy was like this massive football player kid, and he was so strong. How do you think the girls strategized to break a boy off of the clump of people?
I'd probably gang up on him.
Yes, you see what happens. It wasn't one girl trying to do this alone. She took all of her friends, and they would all grab one kid, and they would yank him away. And then you'd have one less person in the clump, and then they would grab another person, one less person in the clump, and eventually they would break them all free.
Wow.
And that is essentially what is going on here.
That's quite the game. I'm not sure I ever played that one.
Yeah, one of them youth group games, yeah. And so the water molecules, you might notice there are lots of water molecules surrounding a particular, let's say that's a chloride ion or whatever, sodium, and it has to have lots and lots of them to break it free. Because technically, if you recall, ionic bonds are very, very strong.
Mm-hmm.
And to break them, even though this water has this sort of, it is a weak kind of attraction, but if you have hundreds of them or tens and 20s of them, it's enough to break them apart.
Yep.
So that's how ionic compounds dissolve in water. What about these polar things dissolving in water? How does that work? So can you think of a polar molecule, Mr. Sims, besides water?
How about ethanol?
Ethanol is CH2OH. Now it's almost better to kind of look at how it looks. It's CCOH. It has a pair of electrons on here, and these little lines represent hydrogens. Now, because the oxygen is more electronegative right here, the oxygen, he's going to have a what?
Partially negative charge.
So he's going to be partially negative, and that's going to make this side partially positive. So if I have a water molecule, I'll draw a water molecule. Remember, that's old Mr. Mickey Mouse, but I'll draw it with the stick figures. That's easier. And he's got an extra couple pairs of electrons. The oxygen will be slightly negative because he's the most electronegative, and the hydrogens are slightly positive. And so what's going to happen here is when we mix these two together, the alcohol will dissolve in the water because this slightly positive is attracted to this slightly negative, and it makes a what? What do we call that here?
That's a hydrogen bond.
This is a hydrogen bond. These are all called, by the way, intermolecular forces. There are hydrogen bonds, dipole forces, and London dispersion forces. Because these are H's and O's and stuff, this is an O connected to an H in both cases, that makes this a hydrogen bond. So when a polar thing dissolves in a polar thing, it has to do with the attraction of the opposite ends of polarities, this end right here and this end right here, to each other. And so that's why they dissolve.
Yep.
So that's kind of a good picture.
Mr. Bergmann, can you refresh our memory as to what elements create hydrogen bonds?
That's a good question. Hydrogen bonds, don't get this mixed up with hydrogen bombs. They are different ballgames.
Yes.
Hydrogen bonds, it is hydrogen. It must be connected either to F, O, or N. fluorine, oxygen, or nitrogen. That means you have HF. Actually, that's the only compound because that's kind of a done compound. H somehow connected to an O. Lots of things could happen after that. And an N connected to an H, and lots of things could happen after that. And in fact, the way we remember this, of course, is what did E.T. say when he said,
phone home.
So if you phone, F-O-N, phone and home for hydrogen.
That's
so
assuming
like,
our students have actually watched E.T.
It is an old
We're
movie.
really dating ourselves here, Mr. Bergmann.
Well, I'm old, so I know that, and I think it came out when I was in high school.
See, I think I was 3 when it came out. I'm pretty sure it was about 1980.
Yeah, 80 sounds about right. High school. I was in high school in
1980.
1980. I was in high school, going to the senior prom and all that stuff. And
Oh, I'd like to see that
Sam's-
picture.
Oh, you should throw.
Actually, I've got my prom picture. I had to bring that one in too. That'd be kind of fun.
That would be interesting. I have it. With Ginny James was my prom date. I remember that. Short little gal. Okay, I'm short. That means she's super short. Okay, nonpolar with a nonpolar. Basically, here on this thing, they essentially sort of just mix. So if you have something that has no attraction, it can slide through. It's almost hard to draw this because. What happens is they slide because they don't have attraction. So I'm not sure what to draw right here.
Yeah, they just kind of bump into each other, and there's just these tiny little moments of attraction to each other, and it's just enough to make them stick together.
Yeah, it's hard to kind of draw a picture. This is a good picture that's in your notes. One thing, actually, let's say one more thing about polar and nonpolar. How do they do when they dissolve in each other, Mr. Sams?
Polar and nonpolar, when we mix them together, they do not mix. We say they're immiscible.
So polar and nonpolar don't mix. Add this to your notes, folks, and that's called immiscible.
I am. Is there 2 M's?
I think there's 2 M's.
I think there's 2 M's. I-S-C-I-B-L-E. I know that part.
So it's immiscible. That means they don't mix. And of course, the main term that people like to remember is like dissolves like.
So polar things dissolve in polar solvents. Nonpolar things dissolve in nonpolar solvents.
So if I take grease and oil, what would happen there, Mr. Sams?
Those two are both nonpolar, so they're going to mix together.
And what if I took water and I mixed it with salt?
Salt is polar. Well, it's extremely polar, so much so that it's ionic, and water's polar, so those are going to dissolve together. But if you mix oil and water, they don't.
Yes, so in this particular picture, you may not get a very good picture because it's in black and white, and we have it here in color, is that we have 3 chemicals. Here we have water, and what do you know about water?
Water's polar.
So notice that if you look carefully, and it may be hard to see this depending on what kind of a podcast you're watching, there's a line demarcating between this and the C6H14, that's hexane. And then on the bottom we have this thing called CCl4, carbon tetrachloride, and there's a line here. So essentially we have 3 layers of chemicals. So if you know that water is polar, what must be true about the chemical on the top, the hexane?
If they're not mixing, that one's going to have to be nonpolar.
And of course the one on the bottom would have to
Also
be
nonpolar.
nonpolar.
Now the reason they're separating out this way is going to be due to their densities.
Yes.
The thing that is most dense is going to be on the bottom, the next dense thing in the middle, and then the next dense thing on top of that.
But interestingly enough, if I would have put the carbon tetrachloride and I would have poured in the hexane at the first
Those
moment,
two would have mixed right off the
and
bat.
they would have dissolved in each other, and the water would have floated in the top, or not. I don't know. Depends on what the mixture would be.
Yeah, the new density of the new mixture.
I don't know, but anyways, it would work. So they had to, I'm going to guess, have poured these separately.
Yep.
So that's something to note about. Okay, we must move on. Strong and weak electrolytes. Okay, what is a strong electrolyte?
Strong electrolyte is something that's going to completely dissociate when it is dissolved in water. And by dissociate, we mean split up into the individual positive and negative ions.
You know, I like to think of it this way, Mr. Sams. You like my little Bergmannisms?
Oh, these are wonderful.
I know. You see, what's true about all high school romances?
Well, my experience, both personally and through observation, is that they all eventually come to an end.
They all break
up.
And they probably break up because they are held together by a weak...
Pretty weak bond.
You see, remember Miss Ginny James, my prom date? Well, I'm not married to Ginny James today.
No, I'm not married to my prom date either.
I don't think I'd really want to be married to Ginny James, to be honest with you. I'm quite happy where I'm at there now. But, so it's like strong it's kind of a weird deal. Strong electrolytes are held together by weak bonds.
Doesn't sound quite right.
But it's true. And so they just completely dissociate into ions, all of them.
So it sounds backwards, but the weak bonds means it'll just fly apart and it'll dissociate when it hits in water.
And then a weak electrolyte...
They do not completely dissociate into the ions.
We can say they partially
So they partially do. So just,
dissociate.
as a ballpark number, we'll say 1% of it.